we are again with Research Director at CNRS, Pascale Senellart. Thank you very much for joining us and sharing some of your insights in this Congress.
Thank you for having me.
That's great. You're very, very welcome. We would like to talk a little bit about your research to start, and especially because you're bringing to the table some new concepts like quantum light. What's that? Can you tell us a little bit about that?
Yeah, what is quantum light? I mean, if you think of light, you think of a wave, okay? But you can also think of particles. This is what quantum mechanics has taught us. Everything is both particle and wave. And we are used to light as a wave, but light is a particle, and the elementary particle of light is a photon. Okay, and so we play with photons. In my group, we generate photons one by one. We play with them, we try to manipulate them to process the information, and we try to encode the information on the photon. So how to encode the information on the photon? Since it's also a wave, it can oscillate vertically, for instance, or horizontally. This is what we call the polarization. We can decide that this is 0, this is 1, and I can create any superposition of 0 and 1, and this is a qubit. Okay?
Great.
So we play with this concept of quantum light. We generate single photon. We try to make that with the tool of semiconductor, of the industry of semiconductor. So this is the same thing that we have for having a laser pointer. In the laser pointer, you have not a single photon at a time. You have photons that come at random times. We try to fabricate devices. Actually, we fabricate devices which are made of the same material. But when you press somehow a button, you get one photon at a time.
That involves a great precision. And I like the concept that you play with photons.
We play with photons.
That's great. That's great. Another concept, maybe you said something about it, semiconductor quantum dots.
Yes.
What's that? Can you tell us about it?
So if you look at the light around us, the natural light that we have in all these systems, they don't generate one photon at a time. Okay? Generally speaking, you don't get one photon at a time. There is one system in nature that generates one photon at a time. It's one atom. Okay? So in principle, I could just take one atom and give it energy, and it will release one photon. Except one atom is a very small particle, and it needs to be in the vacuum and everything. So it's very hard to, and people can do it, but it's hard, and you need to trap them, etc. So it's very demanding. There is another way to do that, is to fabricate artificial atoms. Quantum dots, semiconductor quantum dots, are 10,000 of atoms in the semiconductor materials that traps carriers of like electrons and behave like a single atom. It's 10,000 atoms behaving like one, and this is what we engineer to fabricate the single photon sources.
It's some kind of trick. You're playing with atoms too.
We are sculpting, we are carving the matter at the nanoscale to create an artificial atom so that we benefit from this quantum physics of an atomic system, but with something that is easy to play with.
And we've read that you found a way to make these quantum dots emit light with very, very, very high efficiency.
Yes.
No? How did you get there?
Yes. So this is actually the beginning of my career. All the topic is how, when you take an atom and it emits one photon at a time, the photon is still a wave that it emits in all directions of space. So when you want to make a device and you want to get the photon somewhere, in a fiber, for instance, how do you do that? And so there is a way to do that. It's a big word in physics. It's called cavity quantum electrodynamics. It's basically a big word to say that you can, for instance, put your atom between two mirrors, like in an elevator. When you're in an elevator and between two mirrors, you have multiple reflections of yourselves. It actually shows that you can trap light in between the mirrors. So we trap light in between the mirrors. We put the atom right in the center. And when you do that, it's been shown by theoretical papers 80 years ago, almost, that actually you can force the atom to emit the photon in one direction, the direction defined by your mirrors. So we do that. We actually fabricate this artificial atom, and we also fabricate mirrors around them. And when we do that, we make sure that the photon is always emitted in a very well-defined direction where we can collect them in a fiber.
And at a very, very small scale, that's crazy. That's really surprising.
I should add something, actually, because this is one of the challenges. But if we want to use the photons to play with, to fabricate something useful for quantum technologies, which is the topic of this conference here, how to harvest quantum properties to do new applications, you need more than just having the photon emitted in one direction. You need also to make sure that the system is in a very quiet environment where nothing vibrates, nothing moves, no charge fluctuates. So what we also have done over the last decade is to make use of all the tools of optoelectronics, voltage control, all kinds of things, to make the system quiet and have highly pure quantum single photon.
It's almost poetic. It's beautiful. In fact, you have been able even to create entanglement between those light particles. What does it mean? How can you use that, and what's the idea behind that?
Yeah, so you know, in the second quantum revolution that we are all working towards, we want to create superposition and entanglement. Entanglement is the idea that you have two particles that have a common destiny. We love photons because photons have no charge, no mass. So they don't interact with the environment. So once you release the photon is just completely protected from any kind of decoherence. You know this word that we talk about all the time in quantum stuff. We don't want it to decohere. It means that we don't want it to interact with anything around it. So we love photons for that. But we need to untangle them. Okay? So this is a challenge for the optical quantum technologies, untangle photons. So the way we do that is actually in our artificial atom, we can trap a charge, an electron. We can trap a single electron. And this electron, you know, in this quantum physics, there is this elementary magnet, which we call spin. And the spin can be up or down. And actually, we can use the fact that the spin can be up or down. And when it's up, it will emit some kind of light. And if it's down, it will emit some kind of, another kind of light. And actually, we use this spin to untangle several photons. So this is something that we published a month ago or so on Nature Photonics, where we show that with just the same devices that we have developed for the last 2 decades, we can only not generate single photon, but untangle photons, untangle in a chain, like a chain of photons that are untangled all together.
That sounds like something you can manage in the lab, but sure, it's a big hurdle, a big complication to bring it to applications for the real world. How is it going to be implemented in these optical quantum technologies that you're envisioning?
Yeah, so I mean, you presented me as a research director at CNRS, but I'm also the co-founder of a company, Quandela, that we created in 2017 to first commercialize our single photon sources. So in the last 6 years, we have done this tremendous work of transforming something that is a lab experiment, basically, into a product. And so we've done all the engineering that now allows us to commercialize some kind of standalone single photon source. And it requires a lot of engineering, thinking differently, but it's coming, and we have now commercialized multiple sources worldwide. Wow. And we are making the system every day smaller, more easy to use, user-friendly, etc. And on the untangled photon source, what I love is that all the effort we've done for the single photon, we don't need more to create entanglement. We just need to add a little magnet into the structure to play with this spin, and we will generate entanglement from all the same hardware and technological effort that we've done just for the single photon. So this is really exciting.
And you make it sound easy.
It's not easy. In Quandela, there are 70 people now working to do that. It's a lot of work and exciting work where you have to combine engineering, solid-state physics, quantum optics, and control, software, and all that.
So it was a big transition in terms of work and how you do that, I guess, no? The kind of focus that you're having on the work. And how did you live that? Because that's a huge step, going from academia to industry.
I'm in both.
In behind. Maybe that's more painful. Even.
No, it's fantastic. It's very time-consuming. I won't lie, it's a lot of work. But it's super exciting because I have still 2/3 of my time focused on the fundamental challenges that we need to overcome, or the fundamental questions we need to address, solve, etc. But then there is the other part of my time where I work with a company where I help guide the engineering development, the technological development, and we start using our photons to fabricate real stuff. Like in Quandela, we have built a full stack small-scale quantum computer that is on the cloud. And when you do this kind of stuff, you learn a lot, and interacting with the people doing the software, the algorithm, etc. And there is another stuff that is really, really cool, is that there is this positive feedback loop between the fact that in my lab we do the proof of concepts, okay? And this paper I was mentioning about entanglement, it's really a lab experiment with a bit of complex optics, and we didn't know where we were heading, but now it's working. So now we are discussing with Quandela engineers, like, okay, this is how it can be done. How will you transform this and make it reliable, better, more systematic? And they do that, and then when all the engineering they do comes back to us in the lab and help us do the next step, the best.
You have the whole loop. Huh?
The whole loop, and it's a positive feedback loop between research, industry, engineering, research, etc. It's
Great.
really, really cool.
Great. And maybe now that we're approaching the end of the interview, I would like to get a little more personal. No?
Okay.
And I would like to know, when did you realize that quantum phenomena would have such a big role in your life? Because I guess it's not something that you decide from one day to the other. You wake up one morning and say, wow, I'm going to go quantic. How did it happen?
Yeah, well, for me, it's a bit like how it happened. I always knew I wanted to do science as a teenager. I already spent my vacation in some radio astronomy center. I mean, these guys were very kind to host me, and I was going there. And I thought back then I would do some astronomy. And I rapidly realized that stars are too far away. It's very contemplative and very mathematical research. And actually, I encountered quantum physics in a weird situation in an exam. I mean, there is in France this very hard competition to enter some school. So, École Normale Supérieure of Lyon. I had two people asking me questions to get in. I had two examiners asking me questions and asking me to think of what happens if you try to know, you know when you send light into two slits. Mm-hmm. If you think of a wave, of course it goes through the two slits, right?
Yeah.
Because it's a wave. But if you think of it as particle, it cannot go both ways. Okay, and there is this beautiful experiment, thought experiment, that tells you if you try to know where the photon went through, you destroy some interference phenomena. And they made me think of that during 1 hour with the little tools I had as a second year after baccalaureate. And it was fantastic. I was like, it blew my mind. I was like, I want to do that.
You got lost into the quantum.
I was like, wow, this is so cool, and I want to do that. And after that, I was like, I want to do quantum. That's it.
Yeah, because as humanity, we're quite used to look upwards to the stars, and when we look downwards to the really, really small phenomena, it's also fascinating.
It's super fascinating, yeah, and there is so much to understand.
Great, great. And because you have that experience yourself, what would be your recommendation for a young researcher that is starting his career and is looking for a topic to focus on? What do you think is the way that they could follow?
Okay, I could give you two answers. I could give you the Quandela answer, light is cool, come, would be the one answer. I will give you an answer more as a mother, or the answer I give to most of my students. The topic in quantum, I think, are all fascinating. Find the topic that of course, is interesting for you, but the right people to work with. There is the human aspect in all this research that you do is, in my perspective, most of the time more important to find a mentor that inspires you and that you trust than a very specific topic. And I think there is so many things exciting to do in quantum that this is what you really should seek for.
So human relationships, look for the right people.
I mean,
and the path will come.
Of course, high-level scientists, etc. Of course, go to where it's interesting and busy, etc. But it's not the only criteria. Definitely not.
Right.
And the research environment where you will work is really important.
Great. Another topic, and maybe to finish the interview, that you've mentioned in some interviews that we've seen, is about the ethical implications of all that we're doing. Changes are coming so fast, there is the promise of big applications in the near future. Are we thinking enough about that? Reflection about the ethical implications of all that technology?
I think this topic is somehow very general. I mean, it's true. I mean, this challenging question is even more relevant right now for artificial intelligence than it is for quantum. But quantum is supposed to help artificial intelligence, so we cannot ignore that.
Maybe we should have started before with artificial intelligence.
It's a lot of very tricky questions. I think physicists are not the best person to evaluate the potential of application. I mean, if you think back in the days, the people inventing the laser had no idea that it would be used everywhere at some point. They thought it would be a lab experiment, that's it. So we are the worst people to anticipate. But I think our responsibility is to provide what we know to the people who can imagine and anticipate what comes. And I think, of course, we need to do that. In quantum, about ethical stuff, there is this, I mean, I am very concerned personally by climate change, okay? And I'm developing very costly technology, semiconductor, etc. So at the first sight, it seems like that's going a very good job at meeting my concern in terms of climate change. But at the same time, there is some real possibilities that what we are developing here may provide some energetic advantage. So there is this dimension. Of course, there is always this uncontrolled effect that if you make something less needing of energy, you may use it more. But it's a very complex topic. But I think we are aware. I think we should, as experts, provide our knowledge to help the people who are used to ethical questions and imagine what could come out of it, anticipate.
So there is even more relationships needed, more human relations
with
other areas of thought.
And the gap for the language with these people will going to be is a challenge that I think this quantum revolution is helping, because we are closing the gap with different communities, businessmen, etc. So we're getting used to describing our technology to people who are not in the science business, and this will help probably discuss these ethical topics.
Let's do it. Let's keep on thinking about it. Let's keep on working, and hopefully next year at the Quantum Matter conference in Donosti, you'll have new advances and new ideas to share.
Sebastian?
Yeah, Donosti is the name in
Okay,
Basque.
sorry.
That's fine. I hope we'll meet you there, and
I
you'll
would
have
be
great
happy
news
to.
and great new ideas to share with us.
Thank
you
you
very much for your time.
Thank you very much.
And for you watching this video, please look for the rest of the interviews. A lot of keynote speakers sharing their knowledge in the channel. Thank you.